Hello, everyone. Welcome to the course Principles and Applications of Mechatronic Systems. I'm your instructor, Xiang Jiwen. Today, we will begin Chapter 3, focusing on speed detection sensors in mechatronic equipment. These sensors constitute a crucial part of sensor detection technology. This knowledge is widely applied in industrial production and automated control systems, so I hope everyone will listen carefully. Let us begin with the tachogenerator. When a rotor coil located in a permanent magnetic field rotates with the mechanical equipment at a speed v, according to Faraday's law, the coil cuts through magnetic field lines and generates a no-load induced electromotive force E0 at both ends. The formula is E0 equals C sub E times phi naught times V, where C sub E is the voltage constant and phi naught is the magnetic flux. Please note that this formula is essential, as it shows that the output induced voltage E0 is proportional to the rotational speed V. Therefore, by measuring the output voltage, we can determine the rotational speed. In practical applications, tachogenerators are often connected to the servo motor shaft to provide speed feedback. Tachogenerators are mainly divided into electromagnetic type and permanent magnet type, each with its own characteristics and applicable scenarios, which you can explore in greater detail later. Next, let's learn about the photoelectric speed sensor. First, we need to understand its operating principle, which involves the photoelectric effect. The photoelectric effect includes external photoelectric effect, internal photoelectric effect, and the photovoltaic effect, with the photovoltaic effect being a type of internal photoelectric effect. The external photoelectric effect refers to the emission of electrons from the surface of a material under illumination, as seen in phototubes and photomultiplier tubes. The internal photoelectric effect refers to the generation of electromotive force or changes in resistivity within a material under illumination. Devices such as photodiodes, phototransistors, photocells, and photoresistors operate based on these principles. Taking the phototransistor as an example, as shown in Figure 3.5, when light shines on the base collector junction, electron-hole pairs are generated, forming a base photocurrent that turns the transistor on. A photoelectric speed sensor consists of a rotating disc and a photoelectric switch. The photoelectric switch can be of transmissive type or reflective type. Now, let's focus on the application of photoelectric speed sensors. In practical speed measurements of mechatronic equipment, a perforated disc is usually installed on the rotating shaft, and a transmissive photoelectric switch is installed at the edge of the disc, ensuring that the light path aligns with the hole in the disc. As the equipment rotates, the disc spins along, enabling the photoelectric switch to function. The magnetoelectric speed sensor also utilizes the principle of electromagnetic induction to convert the rotational speed of mechanical equipment into an electrical signal. It has several advantages. It does not require an auxiliary power supply. It easily converts motion into a measurable electrical signal, and it provides high output power, good stability, and a working frequency range of 10 to 1000 Hz, making it widely used. When the shaft rotates, the raised and recessed teeth on the magnetic disc cause changes in the air gap between the disc and the permanent magnet, leading to variations in magnetic flux. The induction coil thus generates a pulsed voltage, where the pulse frequency is given by F equals Z times N, with Z being the number of teeth on the magnetic wheel and N the rotational speed of the measured object. Therefore, as long as we measure the pulse frequency F and know the number of magnetic teeth, we can calculate the speed N. There are several key issues to note during actual installation and use. First, the distance between the magnetic wheel and the sensor should be controlled between 0.5 to 1.2 millimeters. If the distance is too great, significant magnetic leakage may occur, preventing detection of pulse variations and affecting measurement accuracy. Second, the sensor must be perpendicular to the rotation axis of the magnetic wheel, 90 degrees, and aligned with its center to ensure accurate readings. Additionally, when the number of turns of the sensing coil, the size of the air gap, and the strength of the permanent magnetic field are fixed, the pulse voltage amplitude output by the sensor depends solely on the rotational speed. If the measured speed is too low, the output pulse amplitude may be too small to detect reliably. In such cases, signal amplification or conditioning is required before output. This is commonly encountered when measuring wheel speeds. Today, we have studied the tachogenerator, photoelectric speed sensor, and their applications in mechatronic speed measurement. I hope everyone will review the material carefully after class and fully understand the operating principles and application points of these sensors. That concludes this lesson. Thank you for listening. See you next time.